Okay, so I have seen enough and I have heard enough about people saying that, oh, there are no applications for integrals. Well, today is that day that we get to go over what I think is the most applicable form of why we use definite integrals. In this case, in the average value of a function. That's right. Oh, imagine that, learning math for real life applications. Well, today is that day. And so we have just a very simple equation to go over, and it will look something like this.
Hey, look! It's because of you!
That's right. So we have our equation right here as the average value of a function. Simply put, we still have our exact definite integral that we have been working on for so long for any sort of function going from a to b as the limits of integration. But the most important detail here is that we will be multiplying, or in this case dividing by, the b minus a in the denominator. Okay? Why is that important?
You have to think.
Well, let's see if we can visualize what this looks like. So, if we have any sort of generic function of f of x, and we take the definite integral that we have been going over so far, just in terms of visualizing, I drew it like a Riemann sum. Of course, with an actual definite integral that we have been practicing, is that we do get the exact value of the area underneath the function without any sort of under or over approximation. But like I said, thinking of it like a simple visual here is that we have all these different rectangles. Again, back to the Riemann sum, is that there are basically an infinite number of rectangles. But if there are the subset of rectangles underneath the curve, well, we get the total amount of area. But we have that one little factor right there, the 1 over b minus a as a coefficient to that equation. So what does that mean for us? Again, we have a total area, at least in the most basic sense, area being all of the base multiplied by the height, right? And so if we have some sort of base here that going from A to B to give us that area, and then we just added up all the heights. So now instead of just going one base, one height, we have the total base and the total height, right? We have all of that coming together for this function. Well, what do we just divide by? We just divided by the actual base itself from the result of the area that we started with. Oh dear, what are we left with? That's right. By getting rid of the idea of getting the bases out of the function, well, all that we're left with is just the heights. The heights, the actual values of the function going across from that set limit from a going to b. Well, would you look at that? That is the integral.
So there is no problem.
Right there, at least for us, showing that we can then exclude just the heights, and because we turn this into a full area, then by dividing by the base, we get an average height. Or, in this case, the average value of that function. Isn't that great? Oh yes. Imagine adding up all of the heights and dividing it by the total of the bases. We are simply doing average, but now instead going from the 2-dimension of an area underneath a curve, and we are referring back to it in the first dimension of just an average height of a function. I say that's pretty good. So why wouldn't we go ahead and get to an example problem here of what this will look like for us in that sense?
Oh no, what we gonna do?
The integral is tougher.
More than me and you.
That's right. We have a little bit of a challenging example here where it is asking us the average value of this function, f of x, is split into two parts in this piecewise function of x to the third if x is less than 2, and 4x if x is greater than or equal to 2 on the interval of 0 to 5. And they want to know exactly what that average value will look like. Well, we've got just a few stats for ourselves. We first need to keep our cool because this actually is a very easy application for all the things that we have learned so far about definite integrals. So for one, we need to then set up this equation right there. And so we will use this exactly. We'll just have written down on our side just to know how we can set this up to begin calculating. So to begin with, we have the limits from 0 to 5. As you can see, right? If we were to go about this, we would go, 1 over the 5 minus a 0 as the new coefficient in front of the integral. And now we have the integral going from 0 to 5 for the function f of x dx. But
Wait.
there is a little bit of an issue because this function is not one simple function. The rules are split into two parts if it was less than 2 or greater than or equal to 2, which, as you can see, is right smack in the middle of the interval for which we are evaluating x. A little bit of a problem here now, isn't it? But what about this? Couldn't we split this into two integrals, each according to their own rule? Oh, yes, we can. We can then go ahead and instead call this integral exactly instead of going directly from 0 to 5, because that goes through two different sets of values for this function. We can go from 0 to 2 for the function, right where it will end for the first rule of x to the third, and then add it with the remainder of where we need to go from starting from 2 now, ending at 5 where we need to be for the next part of the function. Oh yes, this looks quite promising because we are simply doing addition rule. Now instead, this is for definite integrals. Oh yes, we can take in part what we have practiced so far, that we can manipulate the limits according to the rules that we've learned so far. If we have a function that starts from 0 to 2 and then picks up again from 2 to 5, that will be exactly the same as if the function just started from 0 going all the way to 5. We just need to take this little technical step here so that we understand which rule will apply to which definite integral. Not so bad. So with that written down off to the side as our note, we can then go ahead and start plugging all of that in to our equation here for the average value for that function. So let's go with 1 over 5 as the new coefficient waiting for us. And then we have all of this to solve first. That first integral going from 0 to 2. Now the rule for this function going from 0 to 2 will be the top rule of x to the third power. And then we need to add that with the rest of the integral going from 2 to 5, this time of only going of 4x for that rule. So 4x dx, like that. Okay, now this looks like something we can definitely do after all of our wonderful practice. So let's leave that 1,5 there. It is simply not checked out of the line on the store yet, but we have these two integrals that we can simultaneously solve for. So our first order of business is that we have x to the third power, which means it will be x to the fourth, now divided by 4 as its new coefficient. And we must evaluate those limits from 0 to 2. And the same will happen this time here with 4x, meaning that we get 2x squared as the result of that integration, with the limits going from 2 to 5. Okay, making sure we keep those parentheses on the outside such that that 1/5 will be multiplied at the end. So let's go ahead and start solving for those limits. So to begin with, x to the 4 over 4, which is going to be a nice 16 over 4. and then subtracted by an easy 0 because of the way that has been set up there. And then we need to add that with now instead 2 multiplied by 5 squared going into the place of the x, which would be 25, and then minus a 2 multiplied by 2 squared, which is 4. Just like that. Okay? So with that, we can go clean this up with the last few steps here, is that we end up with a 4 on one side of the parentheses. The 2 times 25 is a 50, and then subtracted by 2 times 4 is an 8. So that ends up with a 42 as a result of all of that multiplication. And so we end up with a nice 46 over 5, finally dealing with the 1/5 at the end, which then if we were to give this into like a mixed number form will be 9 and 1/5 remaining at the end of that. Okay, and that is pretty straightforward on how to use this average value equation. Now, one thing to keep in mind is that for the students taking the exam in a little bit of time here, is that you must memorize this actually. Yes, the AP Calculus test, they will not give you equations, especially for something like this. They expect you to remember this, of understanding what this means, to keep that coefficient in front of there as the 1 over the difference of the limits for average value. Like what is already stated here, they will literally just ask you what the average value is, no other context, because they expect you to know what that looks like. So because of that, I find this very important, and when we get to some word problems, ooh, yes indeed, we'll be getting to some word problems soon enough this week, that there are indeed great applications for this type of equation. So with that, I think that will do it for today. We'll go ahead and pick this up with some last videos on this series for definite integrals before we get to the really serious stuff. So we'll see you again tomorrow, and hopefully you guys are studying very hard for that exam.